Every once in a while, a new kind of transportation comes along and just completely changes how we think about the world. I'm talking about things like the Transcontinental Railroad that stitched a whole country together, or commercial flights that made oceans feel like ponds. Today, we're going to dive into what might just be the next great leap, a train that literally floats on air.
All right, so to get your head around a maglev train, you first have to throw out that classic image of a train. Forget the steel wheels, that whole clickety-clack on the tracks. This train, it doesn't have any. And there's no big chugging locomotive at the front, no giant diesel engine roaring to life. The way this thing gets its power is, well, it's not what you'd expect at all. And here's the real kicker, because it never actually touches the track. The single biggest thing that slows a normal train down, good old friction, is pretty much gone. Which of course brings us to the biggest question of all. If it's missing all those key parts, how on earth does this thing move, let alone at the speeds we're talking about, like commercial jet speeds?
Well, the answer lies in the incredible promise of magnetic levitation. Seriously, it's a technology that sounds like it was ripped straight out of a sci-fi movie, but believe it or not, it's already a reality in some parts of the world.
How real are we talking? Get this. In a test run, a Japan Railway maglev train hit a mind-blowing 374 miles per hour. To put that into perspective for you, that is more than twice the speed of many of the world's fastest conventional trains. We are literally talking about cruising at the same speed as an airplane, but on the ground. A trip from Paris to Rome? That could take just over 2 hours. Insane. But what's really fascinating is that the crazy speed is just the beginning. Because the train hardly ever touches its track or guideway, you get this incredibly smooth ride with way less noise and vibration. Plus, this lack of contact means fewer parts grinding against each other, so fewer mechanical breakdowns, and even fewer delays because of bad weather. All right, so let's pull back the curtain on how all this magic actually works. Let's get into the basic science that makes a massive train float and, well, fly. So if you've ever played with magnets, even just as a kid, you already get the core concept. You felt that weird invisible force pushing two magnets apart, or that satisfying snap when they pull together. That invisible force? That is the entire principle behind this. The official term for this whole thing is magnetic levitation, or just maglev for short. It's really just about using that powerful invisible magnetic force to lift, guide, and shove a vehicle forward. No contact, no moving parts on the track, just pure physics.
Okay, so to make this happen, you really need 3 key ingredients. First, you need a huge electrical power source. Second, you line the track, or the guideway, with metal coils that you can zap with electricity. And third, you attach a bunch of powerful magnets to the bottom of the train itself.
And here's where it all comes together. The system rapidly flips the magnetic polarity of the coils in the track, creating this kind of magnetic wave. This wave literally pulls the train forward from the front while simultaneously pushing it from behind. It's almost like the train is surfing on a continuous, totally invisible wave of energy. Now, the basic idea sounds simple enough, right? Well, the execution, that's where things get really complex. In fact, it's created this pretty fascinating tech rivalry, with 2 main designs fighting for the top spot, mostly coming out of Germany and Japan. Okay, first up is the German system, called EMS. Think of this one like a magnetic hook. The train's magnets are attracted up towards the guideway, lifting it just a tiny bit, about a centimeter. Now the Japanese system, EDS, does the complete opposite. It uses repulsion, pushing the train up and away from the track, which creates a much bigger gap, more like 10 centimeters. The catch? The Japanese train needs to be rolling on rubber tires until it hits about 93 miles an hour before it generates enough magnetic force to actually lift off. So what you've got here is a classic trade-off. The German EMS system is simpler in some ways, but that tiny 1 centimeter gap leaves zero room for error. It needs all these complex sensors working constantly just to keep it from hitting the track, so it's not as stable. The Japanese EDS, on the other hand, is way more stable because of that bigger gap. And it uses super efficient superconducting magnets. But those magnets need super expensive cryogenic cooling systems to work. Oh, and it still needs wheels to get going. And all of this brings us from the super cool world of engineering to the harsh reality of economics. Because for all its brilliance, maglev technology has one giant glaring obstacle: the absolutely staggering cost. I mean, just look at this chart. The price tag is just enormous. Building a maglev system can cost up to $200 million per mile. And that's not just for the fancy magnets. It's the cost of building miles and miles of a guideway that has to be perfectly aligned, down to the millimeter. As you can see, it can be several times more expensive than even traditional high-speed rail. And that, right there, is the heart of the problem. As critics have pointed out for years, a project that costs maybe 5 times more than a conventional one is just an incredibly tough sell to, well, anyone. This one factor has pretty much been the nail in the coffin for dozens of proposed projects, especially in the US and Europe.
You know, the history here is really a mixed bag of promising starts and some very public failures. The very first commercial shuttle actually opened in the UK way back in 1984. But since then, there have been major setbacks, like a tragic accident in Germany and a failed $16 million university project in Virginia that really stalled the momentum.
So, after all that, after the high costs and the setbacks, where does this technology go from here? What's the next stop for the floating train?
Well, the answer, pretty much without a doubt, is Asia. While the West has kind of stalled, countries like Japan, China, and South Korea have gone all in. Today, all 6 of the world's operational commercial maglev lines are there. Japan is in the middle of building a massive line from Tokyo to Osaka, and China is rolling out all these driverless, urban versions for its crowded cities.
And then, what's the next big leap? You've probably heard of it, the hyperloop. The concept is actually built on a very similar idea of magnetic levitation. The key difference, the big innovation, is putting the whole thing inside a sealed, near-vacuum tube. By sucking out all the air, you get rid of air resistance, which is the biggest source of friction left. And that could, theoretically, allow for speeds that are even faster than what we've seen.
So that leaves us with this one big, fascinating question. Maglev is this proven, almost magical technology that offers unbelievable speed and efficiency. But its astronomical cost has kept it stuck on the drawing board in most of the world. So, what do you think? Is it a brilliant idea that just missed its moment, or is it the true future of travel, just waiting for the right time to finally lift off?